In today's session, let me learn about the other PLD, which is one of the PLD, programmable array logic. In last class, we learned about programmable logic array, where your AND inputs as well as your OR inputs are programmable. But whereas in programmable array logic, so you have only the inputs of your AND gate is programmable. So it means the product terms are programmable, where your sum terms are not programmable. So your OR inputs are not programmable. So whatever you connect your output of your AND gates as an inputs to the OR gates are not programmable. They are said to be the fixed OR array or fixed connections. So you have your fixed inputs on your OR gate. And now, so let me see that example. So here I have here 4 inputs. So these 4 inputs, so tri-state buffer I have taken. So this first line indicates here uncomplemented input of I1. So bubble input line will indicate your I1 bar. So 1 and 2 belongs to the input I1 and uncomplemented variable of I1 and complemented variable of your I1. So here 3 4 indicates I2, I2 bar, 5 6 indicates I3, I3 bar, and 6 7 indicates here I4 and I4 bar. So here like this, so they were connected. So here we connected those inputs and their complemented inputs as your vertical lines. And here we can implement 4 number of functions using this PAL. So in this PAL, so each function should have your maximum 3 AND terms, and those because we connected a 3 wide OR gate, so where these 3 AND terms are connected as your inputs to the OR gate. OR gate output is obtained from your OR gate output. We can obtain your functions. So as here 4 functions are there, so maximum you can obtain your 3 product terms. If you are not going to use that product term, one of the product term, so if you have in your minimal expression of your given function only 2 product terms are available, so then the last one which should not be used. So we cannot use that last AND gate which is on your third AND gate. So they are to be unused. Unused gates or inputs are not connected. So hence, so these are denoted as here. This is not used means. So we are going to mark with a cross mark like this. So we can implement your Boolean functions using your programmable inputs of your AND gates. So only AND terms are programmable where your OR gates are fixed. So hence here we have been connected the multiple inputs on your each OR gate where it is having 3 AND terms. Now let me do one example to implement your PAL. So I have 4 functions here with the 4 variables of A, B, C, D. So before we are going to implement these functions, we need to minimize your Boolean functions using your K-map method. Upon having that product terms which are minimal expression, which are in sum of product form, and those after obtaining those sum of product form based on your product terms, so we have to draw the PAL table. Now, so let me first minimize your functions. Thereafter, we will move to your PAL table. So first, so let me move to your W equal to sigma m of 2, 12, 13 is a 4-bit 4 input variable which are A, B, C, D. So I took your 16 cells. So now mapped your function by placing their minterms as they have given sum of minterms. So we put logical ones on your corresponding cells. So now second minterm is 1. So we placed on your second cell. So which is a 1. So along with this 12, 13 are also minterm. So upon mapping your function, then we will go for the minimization. 12, 13 can form a 2 square adjacency which is called a pair. Now that pair can eliminate one variable which is not common for these 2 minterms. For this 2 minterm, the not common variable is D. So hence that was eliminated from the product term, and the common variable for these 2 minterms are AB along with column wise C value is common where C value is 0, hence we represented that product term as ABC bar. Next, So we have a minterm 2 which doesn't have any possibility of pairing. So since that it is called as your isolated minterm. Now that isolated minterm product term is A bar B bar C into D bar. The same manner y is equal to x is equal to sigma m of 7, 8, 9, 10, 11, 12, 13, 14, 15. So first we'll map your function. Upon mapping, we'll go for your minimization. So mapping your minterms, so means placing the corresponding values. So 7, 8, 9, 10, 11, 12, 13, 14, 15. Upon mapping, so we have a 8 square adjacency which can form an octet. So 8, 9, 10, 11, 12, 13, 14, 15 can form an octet. So that octet can eliminate 3 variables from its all the minterms which are not common. Only the common variable is here, it is A. So hence A will come as a product term of minimal expression upon forming a octet in your given expression. Next, there is only one minterm is available, and in order to minimize that minterm, I am using your already covered minterm in your octet. So upon using this, we can form a pair. So a pair can eliminate one variable, and the common variable is row wise it is B, column wise it is CD. So both are logical one, hence a product term. After minimizing your pair, we have your BCD. So minimal expression of your x function is equal to A or of BCD. Y is equal to sigma m of 0, 2, 3, 4, 5, 6, 7, 8, 10, 11, 15. Mapping a function. Upon mapping your function, so we could observe here, we can form a 4, not 4, 3 square, 3 number of 4 square adjacencies. So now, so this belongs to your first quad because all are at your corner cells. So now corner cells can form a 1 quad 1. So quad 1. So column wise this belongs to your quad 2. And now row wise, so this 4 belongs to your quad 3. So with the 3 quads we can cover your all the minterms. So quad 1 row wise, the common variables are B value is 0, so B bar. Column wise 0 0 CD value, and here 1 0. So D value is common and the assigned value on D is 0. So hence B bar D bar. Next, here we can form another quad, so which is column wise. So column wise common variables are CD. So we placed your CD product term as your minimal expression of 4 square adjacency. Next, row wise these 4 also adjacent. So since it is 4 is adjacent to 5, 5 is adjacent to 7, 7 is adjacent to 6, 6 is also adjacent to your 4. Hence, so we can form an quad. So this quad can have your common variables which is AB, where A value is 0, B value is 1. Hence it is A bar B. So your minimal expression of your given function y is equal to B bar D bar plus A bar B plus CD. The same manner Z is equal to, so 2 pairs and 2 isolated minterms. Now these 2 pairs are having the minimal expression is AC bar D bar ABC bar plus, and the 2 isolated minterms are A bar B bar C bar D, A bar B bar C D bar. Now when I am observing carefully here, my function minimal expression of W is ABC bar plus A bar B bar C D bar. Here I can have that minterms are repeated in my Z function. So hence I can replace or I can connect my output function of W as your one of the input of your Z to the OR gate, and then so that must be ORed with your AC bar D bar plus A bar B bar C bar D. So we can obtain your Z function. So along with these 4 inputs, you also have one more input which is your output function W. Hence we have to take your W, and W bar is also one of the input of your PAL. Now, so these are my Boolean expressions upon minimizing. Now let me draw the PAL table. So now in this PAL table, 4 functions. So hence each function is implemented using 3 number of AND gates. So for example, here 3 number minimum maximum is 3 number, but whereas your W function is only having 2 product terms. So hence the third AND gate is unused. So hence we placed a cross mark over there. Next, your function X is having only 2 product terms. so which is A and BCD. So third product term is also unused. So no inputs are connected to the third AND gate. So it is unused AND gate. Next, that third OR gate is also having an inputs of three AND gates. So outputs of your three AND gates are connected as inputs to the OR gate. So whereas here three product terms, so all three AND terms are used. Whereas here Z is equal to W plus AC bar D bar plus A bar B C bar D. Now here also we have the three product terms, so hence the last function Z is implemented using all the three AND gates. Now we can observe carefully here. So when you observe here, we have the proper programmable connections. So the fuse must be connected. So if your input is present, the fuse is blown if your input is not connected. As here in the product term of your W, A, B, C bar we have A value is 1, B value is 1, C value is 0. Hence we connected with a programmable connection of A, B along with C bar input. So hence the first AND gate will give you the product term of your A, B, C bar. So first AND gate will give you the product term of your A, B, C bar. Second product term is here A, B, C, A bar, B bar. So first one A, B, C bar. Second AND gate will give you, because you connected on A bar, B bar along with C and D bar. So second AND term will give you the product term of programmable product term as A bar, B bar, C, D bar, where it doesn't have a third product term. So hence no input is connected to the AND gate. So all programmable connections are blown here because we are not using your third AND gate. Next, so your X function is implemented by using it to a product term. First AND gate only it has to generate the A, so hence we connected only the input A. So A input you connected, so product term will be A here. Next, second product term is BCD, so we connected that particular correspond to the line B input, which is B along with C and D. So hence it will give you the product of BCD. So there is no third product term, hence this third product term is unused. Next, your third function is having three product terms which are A bar B, A value is 0. So we connected to the vertical line of A bar and to the vertical line of B with the programmable connection. And the first AND gate on this third function will give you the product term of A bar B. Second AND gate will give you the function of your CD, and fourth AND gate will give you the output product of your B bar, D bar, as you connected the programmable connection B bar and D bar. So it will give you the product term of B bar, D bar, which can implement your function Y. The same manner. So Z is equal to 4 product terms. So instead of connecting 4 product terms, as you doesn't have your fourth one, so you have already the function W. So that function W is also transferred with the buffer. So and here the which is your ninth line is, so A bar 2, 3, 4, 5, 6, 7, 8. So ninth line is your D, W bar is 10th vertical line. So now here I need to connect Z is represented in terms of your W function. So instead of taking that two product terms additional where W is implemented with the same product terms, so we can directly take the output function of your W. So now we took your W as your one of the product term. So and then we add that with your the other two product terms are A, C bar and D bar along with A bar, B bar, C bar, D. So now we connected A bar, B bar, C bar and D in order to obtain the product term of A bar, B bar, C bar, D on your last AND gate. So like this, so we have to implement your the given Boolean functions using a programmable AND array along with your fixed OR array sessions. So this is the way we will implement your functions. The same way, so in last class we discussed about our PLA implementation. Here I have given one of the example, which is PLA with the 3 inputs and 4 products. As here in the given question, they asked to design with the 3 input and 4 product terms, and available functions are 2 output functions. So now they have given 2 functions. F1 is equal to sigma m of 0, 1, 2, 4. F2 of ABC is equal to sigma m of 0, 5, 6, 7. So for the given functions, this is your truth table. So of your F1 value and F2 value. Let me minimize each function using K-map method. So first function F1 after mapping and combining your minterms. So we got your minimal expression is A bar B bar. So because it is forming a one pair, so A bar B bar. Next A bar C. So because these are in almost it is on right side and left side, so which can form a pair A bar. The common variable is C, so hence it is C bar. Next here column wise we have your pair, so already used minterm. So in order to cover your fourth one, so we are using your already covered minterm which is 0. So B bar C bar. So in the same manner F2 is 0, 5, 6, 7 mapped, and here we obtain 2 pairs along with one isolated minterm. Isolated minterm is A bar B bar C bar, and these two minimal expressions of pairs are AC and AB. But in order to implement these two functions as it is without any complement, so all these product terms when I observe carefully all are different. So hence I require total 6 number of product terms. But instead of 6 product terms, so as in the question given, only you have to use 4 product terms. So we were going to calculate your complement of your F1 and complement of your F2. Now complement of F1 if I wanted to calculate, so I have to cover your max terms. So when I cover the max terms, then I obtain F1 bar is equal to AC plus BC plus AB, or F1 a complement of F1 is equal to A bar R of C bar into B bar R of C bar into A bar R of B bar. So in terms of your PYS form or in terms of your SOP form, you can write it. But so PLA is implemented using SOP form. Hence, I'm just writing as a F1 complement is equal to AC plus BC plus AB. So in the same manner, F2 bar is equal to A bar C plus A bar B plus AB bar C bar, because one isolated minterm and 2 pairs are there. So now when I observe this, so the combination, so to minimize it, so F1, F2, if I observe complement of F2, again I need to take the 6 product terms. But if I observe here F2 value and F1 complement value, there is a possibility that 2 product terms are common from your F1 and F1 bar and F2. Hence, instead of implementing F1 and F2, we will implement your complement of F1 as well as your F2 value. So, if I implement your complement of F1, so it will have AC plus BC plus AB. F2 is AC plus AB plus A bar B bar C bar. So, now let me write your table, PLA table, only for with the 4 product terms. So since the common terms are AB, here AB and AC. So hence here only AB, AC, BC and A bar, B bar, C bar. So if I observe that, so here, so AB product term, AC product term and BC are ones. So A bar, B bar, C bar are all zeros. So in F1 complement, we have 3 product terms which are AB plus AC plus BC. F1 complement, F1 bar, F2 true value is equal to AB plus AC plus A bar, B bar, C bar. So as a PLA is both AND inputs are programmable or inputs are programmable, first AND gate would generate here the product of your AB as you connected only the inputs AB, and second product term will generate your product of your AC. Here it will generate so here it will generate your AB, and it will generate the second product term will generate here AC, Third product term will generate here BC. Fourth product term will generate here A bar, B bar, C bar. But in F1 complement, we are going to use here AB, AC along with BC. So hence here it is connected with the F1. This is this first one, or get implement F2, where it is having AB, AC along with A bar, B bar, C. So your second OR gate will implement your F1, so which is AB plus AC plus BC. Here an additional XOR gate is used. One of the input of your XOR gate is connected with F1, and the second input, if it is connected to 1, it will implement the complement function, which is F1 complement. F1 exclusive OR of 1 is equal to F1 complement. Next, if I connect this second input of your exclusive OR gate with 0, so it implements an exclusive OR function between your F2 and 0 is equal to F2. So F2 true value and F1 complement value we obtain from this PLA table. So this is the way, so we can connect your or obtain your Boolean function using your programmable logical array and programmable array logic.